Hello campers, Dr. Dickey here. All right, I promised you I'd go through terminology and go through the things that people use, the words that people use when they discuss batteries and such. So I'm going to do that. Start with just the real basics, and that is, what's the difference between a battery and a cell? Because you hear people talk about batteries and cells. Cell would be the smallest unit that would be a battery. Like in the 12-volt battery in your car, there's actually six 2-volt cells in there that combined in series as they are makes 12 volts total. So it's a 12-volt battery with 2-volt cells. Now, if you had just one of the cells, like an 18650 battery, then it's a battery when it's by itself. But if I put it into a pack, parallel, or series with a lot of other batteries, then they become cells in the bigger battery. I don't know if that makes sense or not, but that's the way it's going to be discussed. You'll hear people talk about cells. When they talk about cells, they're usually talking about the individual units, the smallest unit that can be a battery in a larger pack of batteries that makes a battery. So a pack, what's a pack? Well, a pack could be usually it's a set of cells that are connected in parallel that may be then connected, the packs may be connected in series to get the total voltage you want. We'll go through series and parallel after we see how you go through some of the battery stuff that you need to understand before we get to that. All right. And also you hear some people use modules too. They might say that they might have bought individual battery packs and they'll consider them a module, and then you hook the modules in series or parallel to increase the capacity or increase the voltage or whatever you want to do. All right. So let's talk about all the things we just talked about that I didn't define. And that is, I'm sure you know about voltage and what voltage is. And voltage, given by a capital V, is a potential. And a potential, anytime you have a potential can be versus something, but it can't be an independent potential. You can't have an independent potential without it being compared to something else. Like if you lift a book off the ground, it has potential energy because it's off of the floor. When you let it go, you see that potential energy get turned into kinetic energy and then it hits the floor, and that's your potential difference between two things. So potential difference, and it's no different in a battery potential. The battery potential is usually given as the voltage of the battery. 18650 battery usually given as a nominal. Nominal means more or less the average voltage in there of being 3.65 or 3.7 volts. So those volts is the potential. That's the difference between the zero potential and the potential of the battery inside there. Then and we'll go through some of the units of that. Then the other thing is you've heard of current, and current is usually given with a capital letter I, and it's given in amps, and we'll go through that in a second. And then there is resistance, and resistance has units of ohms, and we'll go through that too. And then finally, the last thing is watts, and that's power, and so it's usually given a P inside there. So voltage potential. Again, it's a potential versus something, but the potential in this case is 1 volt potential is the difference that will create a joule of energy. Joule is what's used. It's similar. Oh, now I have to try to pull that off my head. I wouldn't be able to do it, and I should be able. 4.184 joules per calorie. You usually hear calories, and when you hear a calorie for food, that's a food calorie, which is a kilocalorie compared to the calorie in science, which is so many joules. Joules comes from James Joule, who saw the connection between work and energy, and so that's named after him for joule. So a volt is a joule per coulomb. Capital C is for coulomb. All right, so what the heck is a coulomb then? Well, a coulomb is actually, you could define it as exactly 1 over 1.602176634 times 10 to the minus 19 elementary charges. Basically what that means is that a coulomb of charge is, so a coulomb of charge is 6.24150,907, I think I'm doing this right, 44 times 10 to the 18 elementary charges. What would be an elementary charge? Well, an electron would be an elementary charge. Electrons have a defined elementary charge of -1, protons +1, and you can have molecules and atoms that also have charges on them. And so if it has a +1 charge, that's a +1 elementary charge. -1, that'd be a -1 elementary charge. And so you can see that a coulomb is a large number of elementary charges, whether they be electrons for -1 or just -1 or +1. It's huge, but it's really not that huge when you consider what a mole is. And a mole in chemistry is how you define the number of things in a mole. And you deal with moles, you count moles and fractions of moles rather than atoms or molecules, because there are 6.022 times 10 to the 23 number of things in a mole, like 144 things in a gross, 12 things in a dozen, that sort of thing. 6.022 times 10 to the 23 number of things in a mole. That's so huge. I think I calculated it one time. If I gave you a mole of dollars, you could spend $1 million a second, every second without stopping, and you would not be able to spend that mole of dollars before the sun burned out. That's how big a mole of dollars are. Okay, so we're talking huge numbers, but of course, we're talking little tiny things when we're talking about atoms and electrons and molecules and things of that nature. So huge numbers. So coulomb is a number of elementary charges. So it makes sense that a joule is produced when a coulomb of charges a coulomb of charges are instituted in there, are used in there. You get a joule of energy from that. That's a certain potential. It drops from 1 joule to 0 joules as a coulomb of electrons or charges go by. Okay. I is for, of course, current. Current is given as a symbol of amperes, and that's an A, but we'll use I in there. And I is the usual symbol that's used for current, and also A for ampere. And that is a coulomb per second. So obviously, amperes is a flow, right? It's a flow of energy. It's a flow of elementary charges, and it's a full set of elementary charges flowing past a point per second. So every second, an elementary number of charges flows past there. That means that is 1 amp. 1 amp of flow of energy, flow of this current that goes by is going to be a coulomb per second in there. So that kind of makes sense. So then resistance. Resistance is given as ohms, which is typically given also as a symbol of the capital, the capital ohm symbol inside there. And that's going to be obviously volts per ampere. I guess I should write that as an I since I'm using that. A and I gets both used for, for current inside. So volt per ampere. Well, that makes sense for resistance, right? And we can get this from the fact that we know that V equals IR, and that's a fundamental Ohm's law that you use for calculating a lot of different things. So obviously then R would be V over I, and that makes sense is that's the amount of potential needed to move 1 amp or 1 coulomb of charges past some point. The higher the voltage necessary to force a coulomb of charges for the amperage for 1 amp is going to be a higher resistance, and that makes perfect sense. The last thing is watts, and that's power. And so power is the rate of change. And anytime you hear rate is always per unit time. Okay, just like this is the rate of coulombs. So the rate of coulombs going past a point, it's in per seconds. Anytime you hear rate, it's per unit time. The unit time generally used a lot is seconds. Some things are very slow, so it might be hours, or it might be days, or it might be years, or whatever. But most of the time, it's going to be given in seconds. So for our power per second, it's the rate of change in something per unit time. It's the electrical energy transferred per unit time. So that's going to be what? That's going to be a joules per second, right? That's going to end up being joules per second. So if we look at power is also given as the voltage times the amperage. So power is the voltage times the amperage. That gives us in watts. The units here are watts, as opposed to ohms. This is amps. And this is, of course, volts. Okay, so if we look at this, does that work out? Well, sure it does, because what's voltage? That voltage is joules per coulomb. And what's amperage? Amperage is coulombs per second. So the coulombs cancel out, and that gives us joules per second. So it works out for a unit of power. It's the amount of energy being moved per second, the amount of energy transferred per second, amount of energy being used per second. So that works out very well, very well. So those are some common terms, of course. I'm sure you know what a volt is and an amp and an ohm and a watt. I just wanted to go through it to make sure that we have a collection of it someplace, because then that's going to be referenced down here for other things. So common terms you'll hear people use when they're talking about batteries, building their own power walls and things of that nature. One of them is going to be a C rate. And that's a capital C, not coulomb, but it's a C. It's given as the C rate. What is the C rate? Well, of course, with batteries, we're always charging them or discharging them. Discharging them to do something, charging them so that the potential's built back up so we can then use it to do work or something like that. So basically, current then. Current is going to be charging or discharging. We have discharging a current at a given voltage, which gives us the power, and we're going to be charging them at a certain potential, at a certain current that give us a certain power into our pack there. So current is often expressed when you're talking with things like this. It's often expressed as a C rate. And what is the C rate? Well, the C rate is just the discharge of the battery or charging of the battery relative to its capacity. And we'll get to capacity in just a second. So let's say I had a battery that had a capacity, total capacity of 2.5 amp hours. That's how capacity is typically given. It's given in amp hours. So you can understand that that's a capacity. If I had a container of something like this and I had it filled with so much stuff, and let's say if I was letting it flow out at 1 milliliter a minute, and it took 20 minutes for all that to come out, then it would have a capacity of 20 mils. And it's the same sort of thing here. If the battery has a capacity of 2.5 amp hours, that means it can discharge at 2.5 amps, and it will take an hour for its capacity to be totally discharged. Again, units of time inside there. This one would be a minute. The other one could be, and this one, other one's an hour. And a lot of times on the battery, it's given as milliamps per hour, but milliamp, is just 1,000 is a thousandth of an amp. So 1,000 of them is an amp. So if it's 2.5, if it's 2,500 milliamps, that's really 2.5 amp hours. And so we have it in amp hours. So that's our capacity. So our C rate. So if we had a battery that has a capacity of 2.5 amp hours, then if we were to discharge it at 2.5 amps, a current flowing out of it at 2.5 amps, and remember amps is coulombs per second, we're doing 2.5 coulombs per second, then it would be able to give us that energy output, that amperage coming out for 1 hour. And that would be a 1C. That would be at a 1C rate. So if I do it at a 2C rate, that means I'm coming out at twice the thing. I would be 5 amps coming out, and it would only be able to discharge that for a half an hour. I think I did mess it up. So if it's at a half C rate, then it's going to be 1.25 amps, and it's going to be able to do it for 2 hours. A lot of times manufacturers will list the capacities, that's in the amp hours. They'll give that in terms of a 0.2 C. That means that they are charging it at 1/5 of what the capacity of the battery is listed as. And you'll understand that we get into some other things dealing with state of charge and everything. So, all right, so that's the C rating. When you hear about a C rating, you can also hear sometimes they'll talk about an E rating, but that's not used nearly as much. It's usually a C rating. C rating is charge or discharge rate relative to the capacity of the battery. Capacity. So what is capacity? Again, capacity is given in amp hours. Most manufacturers will calculate the capacity at 0.2 C. And the reason for that is the faster or slower that you charge it. The slower you charge it, the greater the capacity. The faster you charge it or discharge it, the lower the capacity because of internal resistance and things that we'll kind of get into. But I really can't get into the really nitty-gritty of that kind of things. That's something you'll have to investigate on your own. So what is the capacity? The capacity is the number of amps that it would take to take your battery from 100% state of charge to 0% state of charge. State of charge doesn't mean that the voltage is 0. it means that you're taking it from a fully charged state to a fully discharged state. And of course, you would never discharge a battery to 0 volts because it would cause irreparable damage inside the battery when you do that. So, state of charge, capacity is from the state of charge. If you go from the 100% state of charge, fully charged battery, down to the cutoff voltage, that's typically what it's called, the voltage at which you will stop discharging the battery so that you don't cause damage. 18650 batteries, generally the top end's 4.2, the bottom end's around 3 volts. Okay, so that would be taking it from a state of charge of 100% to 0%. However many amps it takes to do that, that's what's going to be your capacity, your amp hours in there if it takes an hour to do it. So typically 2.5 amp hour battery if you're charging it at half an amp and it takes 5 hours, that would be a 2.5 amp hour capacity battery. Does that kind of make sense? That's where your capacity comes from. It's the amount of sort of energy it can hold, the charge that it can hold inside there. Energy is given in watts, of course. So in energy, there's also an energy capacity that is given in watt hours. And watt hours, of course, would be the voltage, the nominal voltage. Really, to get the correct power and the correct capacity, you'd have to integrate underneath the curve from the discharge rate to what the actual potential was at each point along the way. But most people just use the nominal voltage. If I've got an 18650 battery that's in a 7 configuration, that is 7 batteries put in series, then they have, typically we would consider that to be around 24 volts, even though if you figure it out, it's much higher than that, but you take from the top end to the bottom end and use what the nominal voltage, I think even the nominal voltage of that is higher than 24. We'd have to calculate it out. But you don't usually go through the trouble of integrating the area underneath that curve because as you're discharging the battery, of course, state of charge is going to have an effect upon the voltage that the battery has, and so it can change things. So energy capacity would be given in watt hours. Capacity for the battery would be given in amp hours. And then you might as well throw in the term that there are secondary and primary batteries. Any rechargeable battery is a secondary battery. Any non-rechargeable battery is a primary battery. Okay, so those are a lot of terms that are used when you're talking about batteries and things of that. So some other ones, state of charge. State of charge is given in percentage, and it tells you where the battery is sort of in percentage of its maximum capacity. What capacity does it have relative to its 100% capacity? Same thing as charge. That's going to be the same as the percentage of the charge between 100% state of charge and your cutoff voltage, which would be 0% state of charge. It's given as a percentage, and it's what is the state of the battery. Is it fully charged? Is it halfway charged? Where is it between its cutoff voltage and its maximum voltage, which is also its complete capacity and 0 capacity? Because once you get to the cutoff voltage, you consider that there's no more capacity, no more useful capacity left in the battery. Depth of discharge, it's another term that's also used. It's kind of the reciprocal of the state of charge, right? Depth of discharge is how far do you discharge it? What is the percentage that you have discharged of its capacity? So depth of discharge of 80% would be a state of charge of 20%. Okay, so that kind of gives you the discharge capacity. And their terminal voltage. These are some things that are important to know. Terminal voltage. Terminal voltage is what voltage you measure at the terminals of the batteries. Now, this is going to vary when it's under load. It actually varies a tiny bit when it isn't under load, but that's a little bit harder to address because the battery has some sort of internal resistance, therefore, to even measure. But typically, when you measure the terminal voltage of the battery, you're putting your DMM on there, and if there is a load underneath of it, then the battery's terminal voltage is going to drop down because it's going to be taking that voltage to push the amperage through. The voltage will drop down. Open circuit voltage is when you're measuring the voltage of the battery when there is no load on it, technically. DMMs have very, very high internal resistance, mega ohms of resistance. So you can consider, and then of course the batteries have very, very small resistance. So you can consider that it's essentially no load condition because the load is so large that it can't really move many amps through it. So Open circuit voltage is measuring the voltage when there's no load. Terminal voltage is measuring the voltage when there is a load underneath of it. And of course, the terminal voltage will generally always be less than the open circuit voltage. And you can kind of understand that. Internal resistance, then. Keep talking about. What is internal resistance? Well, every battery has chemicals in it that are going to move from point A to point B to be able to create this potential, and so there's some restriction for those movements of those chemicals, and there's other things that happen in the battery that build up a resistance inside there. So every battery has some sort of internal resistance. Now, the lower the internal resistance, sort of the better to a certain point, and that's because if I'm getting a battery and I'm going and I'm using it for some work and it's discharging, then the discharge is going to go through that resistance, and therefore it's going to begin. Of course, the resistance typically dissipates the energy in heat, and that means the battery is going to heat up. So you don't want a battery with a high internal resistance. Even though internal resistance is really what's going on, almost never do anything by internal resistance. It's almost always done by impedance. What is impedance? Well, impedance is usually for AC, more for AC, not for DC. And it just includes the reactance and the capacitance and can't get into all that stuff. But we use impedance rather than resistance because impedance is much, much easier to measure than resistance is. Resistance is a little bit complicated. It's not that complicated, but it is a little bit complicated. And it's going to be voltage, it's going to be state of charge dependent, and things that we don't like. For impedance, which is usually the way the manufacturers list their batteries, impedance is very simple, and I'll show you in a second. We get done with this discussion, I'm going to show you how to do these different things that you need to do to check your batteries before you build a do-it-yourself Powerwall. So measuring the internal impedance is very, very important. And again, it's used rather than resistance simply because it's so much easier to do. Manufacturers list the internal impedance in their batteries, and they do it as an impedance. And it's measured at 1 kilohertz is the frequency at which the internal resistance is measured. People will always say internal resistance, even though really we're talking about the internal impedance of that. Okay. All right. Just a couple more terms. Cycle life. Cycle life is how many times can you cycle the battery before its usefulness is pretty much used up. Now, a cycle life would be from 100% state of charge to 0% state of charge. Each time you go to 100% state of charge and go to 0% state of charge, you damage the battery a little bit, right? It's like anything else. It wears down over time. So let's say for 18650 batteries, I think usually you see 500 cycle life, the cycle life of 500 times or 700 times. If you don't go to 100% state of charge and then down to 0% state of charge, you can increase the number of times you could cycle the battery significantly, maybe doubling it or tripling it or more. So obviously most people, when they're building a Powerwall or something like that with 18650 batteries, you're not going to go to 100% state of charge and then down to 0% state of charge. You're just not going to do that because you can get many, many more cycles out of the battery. So you would want to cycle it very, very minimally if you can, depending on how much energy you need at the time. Specific energy. Well, you remember with rate, anytime you heard anything with rate, it was always per unit time. Specific always means per unit mass. That means usually per kilogram, per mass of some sort. So anytime you hear specific anything, specific energy, specific different things. So specific energy is, like I said, that's going to be the watts per kilogram for a battery. And I think there's a theoretical thing of trying to get 1,000 watts per kilogram is like the magic grail that everyone's shooting for. A kilowatt per kilogram. I may be wrong about that. Maybe 1,000 kilowatts per kilogram, but I think it's a kilowatt per kilogram. And right now they can get like 900 per kilogram. Or maybe that's what they're even shooting for. Energy density. Density, again, is, you know what density is. That's the mass per unit volume. So again, we're at unit volume. So the energy density is going to be per unit volume. And then the final thing is the maximum continuous discharge current. And batteries will have that rated on them. And I'll show you on 18650 batteries. I'm using the LG M26 batteries, and they have 2.6. The manufacturer lists them as 2.6 amp hours of capacity and 10 amp maximum continuous discharge rate. That would be the maximum rate of discharge of the battery that could do it without causing catastrophic damage to the battery. You would never want to get to that because it will cause damage to the battery, and it would heat the battery up significantly due to its internal resistance. But that's the maximum that could be done. So it kind of gives you a general idea of what you want to stay away from when you're building your do-it-yourself Powerwall. You would never want to get up anywhere near to the maximum continuous discharge rate for your battery. All right. So the only other thing left is sort of the forming of the battery with how much in parallel and how much in series, and what do the two different things do. And we'll do that after we look at sort of what you want to do when you go through your batteries to test them. The procedure really is, at least for the batteries I'm using, and generally for 18650 batteries, when you first get them out of the pack, you want to measure the internal impedance, and you want to measure the nominal voltage. Actually at that point, I guess, since you're not really having a load underneath it, you'd be measuring the open circuit voltage, which is going to give you an idea of the state of charge. For 18650 batteries, you usually don't want to go below 2.5 volts, right? You don't ever want to go below 2.5 volts. For the ones I'm doing, I'm actually using more like 2 volts. If the battery's been discharged below 2 volts, I probably think it's had enough damage that I don't want to consider it. If it's above 2 volts, then I'll go ahead and charge it up after I measure the internal impedance. For my batteries, an internal impedance greater than about 38 milliohms is too high, and I won't use those either. The batteries I've been testing generally range between, say, 33 milliohms to about 37 milliohms would be the highest end. And of course, I'll use the lowest ones possible when I build my pack up. So that's the first thing you do. Then you want to check the capacity, and I'll show you how to do that. Now you've got the capacity, you've got the internal impedance, you've got the nominal voltage when it started. It's going to be charged up to 4.2 volts when you're done. Then you set the batteries aside for a month, okay? And after a month, you measure the open circuit potential again, open circuit voltage. It should not have dropped below 4.1 volts. Really, for me, I use like 4.15 volts. Even after a month's time. If it's dropped below that, especially if it's dropped below 4.1 volts after a month or so, then it's going to be self-discharging, and you don't want to put that into your pack, because when you put it into your pack, it's really hard to get those back out again. So you want to make sure that the cells you put in there are good. They're probably under 4 years old. They have they have an initial potential before you start messing with them of greater than 2.5 volts or 2 volts at least. And then you want to make sure that they have an internal resistance that is low, that's within specs that you want. And then you check the capacity to make sure that the capacity is up there at say at least 90% or so, 95%. My batteries, again, these LG 26 batteries are rated for 2.6 amp hours, and capacity testing them, I have most all of them, 100% of them are between 2.598 amp hours and 2.8 amp hours. Some of them go a little bit higher than that. I think that's more a function of the capacity checker than it is the actual battery. But basically, they're all in there at 2.6 amp hours. So they're all pretty much at 100% of their capacity, which is what you would want. So let's look at how we go about doing that, and then we'll go back and talk about parallel and series in building a Powerwall. Okay? All right, so like I said, one of the things you're going to want to do is check the impedance of your batteries. And to do that, you use the special probes. It has 2 probes on each one for the current and one for the voltage. And all you do is you just stick it on the positive and negative end, and it gives you a reading. It tells you the voltage, and it tells you the milliohms. I'll show it to you in a second. Okay, this is the RC3563, and I'll show you what you see. So there you can see it's 4.169 volts, and it's 35.94 milliohms. So measuring the capacity, I have 2 of the Opus BT3100s. You put those in there, and it will show you, and I'll see if it washes out if I turn the light on. But anyway, it tells you what rate it's charging and discharging it, how long it's been charging or discharging, whether it's charging or discharging, and then when it's done, it ends up showing you the capacity of the battery. And I'll show you a picture of that when I get one that's up like that. Okay, so some of the battery's capacity has been determined. What it does is it will charge the battery up to the max and then slowly discharge it. I'd use a discharge rate of about 0.2 C, which is about a half an amp. And it'll discharge it down to the low voltage cutoff and measure how much time it takes to do that. And based on that, it can figure out the capacity of the batteries, which is given in amp hours. And then it will charge them back up, although usually I take them off and use another charger to charge them up so I can keep capacity testing the batteries. Okay, let's finish up everything. We've gone through what you do to test your cells out before you're going to put together your battery. So then you're going to get ready to put together your battery. So your battery is going to be composed of so many cells. And how you arrange those cells has an effect on the voltage of the battery and also the capacity of the battery. So let's go through that. Typically for lithium-ion batteries, 12-volt systems aren't very good because each cell has a nominal voltage of 3.6 and that doesn't go into 12, even when you're talking about a 12-volt system, like for lead-acid batteries, you're talking about a high end of 13.1 volts or something and down to 11 some volts at the other end. So the voltages that you give is sort of the mean voltage or the average voltage or somewhere in that ballpark. Whatever you're running, typically an inverter, will have a range of voltage that it can input, that it can handle. And you have to match your system to that input. If you overcharge your system to the state of charge is whatever you're using, 90% state of charge, and that voltage is higher than what your instrument can use, your inverter, then it's no good. For lithium-ion batteries, typically 7S, 7 in series, gives you about a 24-volt system. 14 in series gives you about a 48-volt system, and those are the typical ones. So let's talk about that. Series and parallel. So if I take a series of cells, and I say a series of cells, I shouldn't say that. I take a set of cells, and I hook them up so that all of the positive ends are hooked together and all the negative ends are hooked together like that. And then, so what is my voltage out here? Well, if these are all 2.5 volts, then it's easy to see they're all going to be the same voltage since they're all hooked together. They're going to be the same voltage. This is going to be 2.5 volts. But if each one of these is 2.5 amp hours of capacity, then by hooking, let's say I hook 10 of these together, it's still going to be 2.5 volts. But if I have 10 of these cells or packs, either way you want to do it, as you'll see in a second, then I'm going to have 10 times 2.5 amp hours, or I'm going to have 25 amp hours. So 25 amp hours. And then you can see that the power of the system, the energy of the system increases, energy being watt hours. So if I have 2.5 volts, remember watts is volts times amps. My amp hours is 25 now, 2.5 volts. Each one is at 25 amp hours, 25 amps possible amp hours. So I'm going to get 2 times 25 is 50, half of 25, 12 and a half. So that'd be 62 and a half watt hours. So you can see how that increased. That's if you do them in parallel. But parallel, all you're doing is taking individual cells and you're making one big cell out of them. Say cell, not battery, because the battery is going to be in series also. So hooking them in parallel, again, making one big cell. Now I take those cells and I hook them in series. Well, it starts off 0 and it goes up to 2.5 volts, right? That's the first one. If I hook the next one up in series, then it starts at 2.5 and it's going to go up to 5 volts. And then if I hook another one in series, it's going to start off at 5 volts and it's going to go up to 7.25 volts. And again, if I hook 10 of those in series like that, I'm going to go, even though each one's 2.5 volts, I'm going to go up to 25 volts total for it. Okay, so 2.5 volts, 10 of them in series, the voltage increases. Now, if these are all 2.5 amp hours, my amp hours is not increasing because they're not being hooked to where the positives are the positives and negatives and making one big battery, so one big cell, sort of. So in this case, my amp hours is still going to be 2.5 amp hours of capacity, but at 25 volts. Again, 2.5 times 25, you can see the watt hours is going to be exactly the same as the other cell that we made that was 10 of those in parallel. All right. So that's how you do it. So series and parallel. If you want to get series, Then if you want to get around 24 volts for lithium ion batteries, typically you're going to do a 7S. If you want 48 volts, you're typically going to do a 14S. That's the way it typically works out. What am I going to do? I'm not even sure yet. I keep going back and forth. I keep thinking, well, I could do 7S. It would be easier for my BMS, and we'll get into that stuff in a later video when we get to that, because then I only need 7 different packs in there in series to make up my battery. But by the same token, maybe I'm going to go 14S and get to 48 volts. But I'm looking to get something around 15 kilowatt hours is what I want as far as my energy capacity of my battery. That's what I'm going to look for. So I'm not exactly sure what I'm going to do, but I'll have to figure it out pretty soon because I processed a lot of cells and it's getting ready time to do it. All right. So thanks for watching again. I'm sure I made tons of mistakes. I know I said how many amps it takes to go in rather than how many hours it takes at an amp rate to go into it. Little things like that, but I'm sure you pretty much got the gist of it. So again, thanks for watching, and hopefully see you in the next video.